All right, so we'll continue talking about receiver design from last week. And I guess before we get started, so I managed to upload the videos from last week in two parts to my Manhattan College YouTube channel. I've put links to those in Moodle. Hopefully that'll work out okay, rather than just uploading them directly to Moodle. And then hopefully I'll get these uploaded a little bit more timely fashion. And then we'll I think the homework on Moodle probably thinks it's still due today. I'll probably make that due Monday evening. I think would be a reasonable time. We should schedule a test soon. Do we want to have that next Friday or
When's the homework due again?
Monday.
Okay.
yeah, and then there's so should we have the test next Friday or a week from Tuesday?
We got 1 week from Tuesday. Nobody else has said anything, so I think the week from Tuesday's have it.
Week from Tuesday? Okay. I want to be sensitive in case you have two other tests that day or something like that. So don't want to overwhelm you, but want to also give you a little bit of time between the test and the midterm, which I think will be in early March. Probably need to check the calendar, but okay, so I'll confirm that, but yeah, be thinking about that, and we'll give some indication of what will be on the test next week, and so you can prepare for that. So all right, so today let's talk about Q functions. I did not go into these in a lot of detail earlier. I don't even think I mentioned them when we covered the Gaussian distribution early on in the class, but it's an important part of tightly related to the Gaussian distribution, and we need it to be able to evaluate the error rates that we're going to see in our digital receivers, because the noise tends to be Gaussian, right? And that's our ultimate limitation is the Gaussian noise in our system. And so we'll need to integrate our probability density function, and that gives us a form that looks very much like a Q function. So we tend to relate those two together, and then you can just look up the values in a table or that type of thing. So and then we'll talk about decision areas. I think we've touched on that at the end of the last session, and then look at some example that is binary antipodal signaling system. So to find a distribution function, one integrates the PDF. So in a form of a Gaussian distribution, we have a PDF of this form with a coefficient out front, and the random variable appears in the exponent in a squared fashion, and we see that the mean is subtracted from that random variable. Of course, in most noise sources will treat as zero mean, and but the variance shows up in both the exponent in the denominator and in the coefficient in the denominator. So this is a Q function that we're defining here, and it's going to be defined with the integral from x to infinity where we've now done a little variable substitution here. So we have a T out front. This is for the describing the probability of a additive white Gaussian noise process with zero mean and a variance of 1. When that probability of the random variable described by that is greater than this parameter x. Okay, and so q is a function of x appears at that lower bound of the integral. All right, so how do we get there? All right, so let's look at f of x, and here this is our distribution for this Gaussian PDF, right? So we're going to integrate this, and we integrate that from minus infinity up to a value of x, right? And so now we put that in terms of dummy variable t, and now we can flip our integration limits around, and instead of going from minus infinity to x, we'll go from x to infinity. And we know with the properties of the distribution function and the total probability being 1, that's simply 1 minus that value, right? So then we do a variable dummy variable substitution where we let u equal this some of this stuff up here in the exponent, and then we calculate du from that. We substitute all that in, so it's just a substitution, and then we can see that this integral over here has that same form as this q function that we defined here. So so now we can take this integral over here and replace that with our q, where that x is now x minus m divided by sigma. So that's nice. It's the m and the root of the variance or standard deviation. And of course, we're 1 minus that too, because of that this first step we did up there. So a few fun facts about Q function. So when you go out this weekend, and you can impress your friends with what you know about the Q function. So this X now is, we describing it as this N noise process, or normal process, I'm sorry, distribution with the mean and the variance. The probability X is greater than some alpha is equal to Q, where we substitute that alpha in the argument. Conversely, the probability that a random variable is less than alpha, we just flip these, negate this term up here, basically. So Q of 0 is equal to 1/2. Q of infinity is equal to 0. Q of minus infinity is equal to 1. And then the Q of minus x is equal to 1 minus the Q of x. So that gets you started. It can help you transform things and cast it to different type of problems and all. So this is copied out of the Procus book, and so here we have a chart of some typical behaviors, but this is where you're going to be looking at. So you can see here at 0, Q is 0.5, and and it gets really small really fast here, right? So you'll use this in the homework assignment. One of the problems is asking you to look at the probability of errors, and and we'll actually talk a little bit about that at the end of the lecture with an example of this binary antipodal signaling. So you'll look up these X values and as an index and grab your Q. For the homework, you don't have to interpolate or anything like that. So, but you might want to use some of these rules as appropriate. All right, so now let's look at decision areas, right? So we touched on this last lecture, and this is the idea that if we measure the symbols at the receiver, and we're estimating the value of that that signal, then we want to map that as best we can to the original symbol that was sent. And then that symbol maps to an M, particular message, and then that maps to a certain set of bits, right? So that's those latter mappings are known a priori. We just need to figure out, all right, if we're measuring some voltage in our system that's representative of a symbol that we've received, how do we know what that original symbol best corresponds to, right? So it may seem easy here, but we'll in general, it may not be that easy, right? So let's develop a mathematical foundation. So we want to define some number M of decision areas such that if R is within a particular DM within a particular decision area, then we can take that R, process it through some function or mapping to a an estimated M, right, corresponding to what symbol was sent. And then we want that. We want to define all these such that that estimated M matches the real M, the M that was sent, right? So remember the little hat or the caret is referenced at the receiver. That's what we're estimating or trying to measure what that value is, not knowing exactly what was actually sent. Right. So looking at a particular DM, then little m, so it could be any of these D1, 2, 3, 4 up to M. Then we have this R within the real set. Now this N here, the exponent, oops, is implying, indicating that I must have timing on accidentally. Sorry about that. The R is a vector, right? So it's some number of points. So that's not overly, it's more of a mathematical subtlety here, that what we're really looking at here is that the probability that the message that given R that was the message was sent is greater than all the other messages where M prime is not equal to M, right? So we're basically saying pick the best M out of those R's. So here, if we have this binary antipodal signaling here, where this is like minus square root of the energy of the symbol, okay, in terms of voltage amplitude, then and that maps to 0, and this is the positive one, and that maps to 1, and these are equidistant apart from the main from the 0 axis here, 0 value of the axis. Then if your signal, measured signal, shows up anywhere in this green region, out to infinity this way, out to infinity, up and down, whatever, that you're going to map that to this M, the symbol associated with this M, or the M associated with that symbol. And conversely, if you're anywhere over here in this teal colored area, you're going to map to that, right? So that seems pretty obvious. What assumption have I made here when I draw this diagram like this? Can you see I've made an important assumption when I've done it this way? It's not terribly obvious, but anyone want to hazard a guess?
You just yell at that. Or just say it.
Yeah, say it. Yeah,
Each signal is equal has an equal probability, right?
Very good, very good. Yeah. So we'll see that that in the general case where they're not equal probable, then this kind of dividing line here is not necessarily right there. Okay, so very good answer. So so what is this really, right? So there's a bunch of math and all, but conceptually we want to choose the boundaries of the decision areas such that we give the receiver the best chance of selecting the correct message in spite of all the noise and other impairments that perturb the position of the received symbol relative to all the other ideal symbol locations, right? So so in this case, yeah, is we saw last week that these constellations at the receiver, they don't look so neat like this, right? They're messy, and the voltage that you're measuring might have some amplitude and phase very different from this, and we're trying to make sure that we map that in the best way we can. So this seems pretty clear, but how can we derive a methodical approach at finding these areas optimally, right? So so we'll do that. We'll look at the decision areas for additive white Gaussian noise channels. So let's start again with this idea that we're going to select our M hat, our at best estimate of the M, by looking at all the different possible M's that it could be, and as an argument into this function, and looking at which argument produces the maximum value of what's in there, right? So that's that argmax operation there, function, is that we're looking to maximize this. But what we're really interested in is the particular M argument that produces a maximum. We're not so much concerned about what that maximum value actually is, rather than we're interested in what the argument is, right? So so now we can do a little bit of simplification here and look at the probability R minus SM, and then we start substituting in. This is the Euclidean mean here, and we stick that up there in this probability density function, right? And so since this is actually, strictly speaking, a vector of n, then the exponents get the coefficient gets multiplied n times, right? And so then we're and these are still vectors up here, so the n is kind of implied in these vectors. All right, so now it turns out that this coefficient here really isn't a function of m, right? So when we're doing this argmax process, it really has no bearing or impact on what that m is, as long as there's nothing like causing it to change sign or anything like that. There's really nothing that can affect choosing which m is the produces a maximum value, right? So let's just drop that, and then we still have this, but that exponential, that's annoying. So let's take the natural log of this thing, right? So the natural logarithm is a continuously increasing function that's non-negative. So we can do that operation again without affecting this result. It's definitely changing the value that we're going to come up with, but remember I said we don't really care what the value of this maximum operation is. What we really care about is which argument produces a maximum, right? So as long as we don't change the direction at which these functions are going, we can do that, right? So we can take the natural log of this probability of which message was needing to be sent, right? The a priori probability of which message is being sent in the system. And now the natural log just cancels out that base E there, but we need to be mindful of that minus sign, bring that down. Okay, so now we just repeating that, now we can likewise take this coefficient out front and multiply it, so it cancels in here. We've got some factors of 1/2 going on, and so again, that's a positive value, so it's not affecting this operation right here. Then we just multiply this out, okay? And now we also note that R, this norm squared here, R is also not a function of M. So we can just get rid of it, right? And this SM squared in the norm process is really the energy of the message, right? So we'll show it as this script E sub M, so the energy of that message, and bringing forth our -1/2 coefficient there. And so then this the -2 cancels out with that -1/2, so we're ended up with R dot product times the S sub M. Okay, so this is really our answer, but we'll simplify it by defining what we call a bias term, and that's going to look at these things here that are more a function of the transmitter design and the overall energy in these in a particular symbol, and we'll call that eta sub M. Don't get confused with like a little n, which we will often use to describe an individual noise sample or a vector of noise samples. This is an eta, so it's describing this bias term, and we're just doing that to simplify so that this equation is really showing this. This is what we're really going to operate over, but we need to be mindful of that bias term. Okay, so I'm going to repeat that up here, and now note that, well, if they're equiprobable, then PM is equal to a constant of 1 over capital N, right? And so now we'll note that these guys are no longer, under this condition, no longer a function of M. So again, we can ignore them. So now we have this argmax of minus this function there. And so now we can deal with this minus sign by changing it to an argmin instead of an argmax. So now we have this up here that describes a general case, but if they're equiprobable, we can use this form down here. All right, so lots of math. What does all this mean? Okay, so this is a diagram from the book, and it don't think that this is like a normal constellation or anything. You wouldn't actually design a constellation this way, but it's handy to describe some of the approaches that's really involved here. So if we go through and kind of interpret the consequence of all this math, these decision boundaries that we're finding now are going to be the loci of all the points equidistant between the nearest SMs, right? So between these 2 points, we really don't care about that point, right? It's far enough away. We're not it's not influencing this decision boundary. So but this is the Euclidean distance between these 2 ideal symbol points, and this is the decision boundary, and you'll note that it bisects that normally, perpendicularly. It bisects the distance between these 2 points, right? Same way over here, this line is bisecting perpendicularly, right? And so you would look at these 2 points, draw that line, draw this line. This line corresponds to bisecting this distance, again perpendicularly. They join right there, so that's intersection of what these things all end up being hyperplanes. Okay, so fun with geometry. In that original case we looked at, the binary antipodal signaling, we only had 2 different symbols, right? And so that defined the decision boundary as a simple line. As you start to increase the number of symbols in your system, then, or increasing m, basically, you're going to go from a line to a plane to hyperplanes, right? So the idea here is that there, the magic that I say, this is bisecting this line, connecting them in a normal or orthogonal or perpendicular manner, that really is originating from this idea that they are equidistant, right? So that's this is kind of the fundamental aspect, and it turns out that maps to this line. So we end up with let's see, so if we have a signal here in our, I'm sorry,
no, it's a sneeze. Sorry.
I'm sorry,
you're fine. Keep going. Sorry,
okay.
Just a sneeze.
Okay. All right, so if this red star is the measurement of the reception of some R, then what we're interested in doing is finding that symbol with the minimum Euclidean distance, right? So we call this a nearest neighbor detector. So we're basically looking for the nearest one. Obviously, it makes sense, right? But now you understand the mathematical foundation behind all of this, and you can see that, yeah, when you get more complex constellations, it's not necessarily intuitive, and we want to be able to ultimately encode this in some software or firmware into a system. And so we need to be able to describe this mathematically. It's one thing to see it with our eyes, but yeah, at some point you gotta write some code to make this happen, right? So all right. Then so we can write this in a vector form now again, and show this with this bias term out here, and showing this, that in general we're looking for a particular decision area that satisfies this such that type of equation here, right? So whatever R you're getting is going to be associated with this this particular decision area, assuming that this satisfies this inequality relationship for all relative to all the other M's. So nearest neighbor detector. Okay.
Professor?
Yeah.
Just a comment. We can't see your mouse.
Oh, you can't see my mouse. Okay. Can you see it now?
Now, yes.
Oh, okay. Okay, I'm sorry. Are you seeing when I'm sharing this, are you seeing my two screens here, two slides? Are you seeing the slide preview? Or are you seeing?
Yeah. You're seeing that one main screen binary antipodal signaling, and then the next slide.
Oh, okay. Okay. So all right, I'll sweep my mouse on this one right there. So okay. So let me go back and describe that one then here. So we have a particular decision area for this particular M. We're going to map to that one. If R anywhere in this real number space is going to be a part of this decision area, if this dot product operation here tweaked by this bias term for this particular M is greater than all of these others, right? So okay. All right, so now let's look at this binary antipodal signaling with now what we've learned. Okay, now that last part, you'll see that I kind of switch between signals and vectors at different times, right? So they're, again, we're really receiving signals, but sometimes it's convenient to work with the vectors, right? So here we're going to talk about binary antipodal signaling. So what does that mean? Well, binary means there's two signals, two symbols, right? So an antipodal means that they're opposite signs. And so what does that mean? That means M is equal to 2, therefore K, or the number of bits that are used to map one of these symbols, is 1, right? So if that bit is 1, it's going to map to one particular symbol. If that bit is 0, it's going to map to the other symbol, right? There's only 2 symbols, so K is equal to 1. So we can say that S sub 1, where M is equal to 1, of T is going to equal some symbol S of T, right? And then S2 of T is going to equal minus that same symbol, right? So it's just negating that symbol. So the probability of message 1 is we're going to represent as little case p, okay? And the probability of message 2, M equals 2, is going to equal to 1 minus p. There's 2 symbols, one of them's got to get sent, so that encompasses the entire symbol space, right? So if the probability of P1 is P, then we know that the probability of P2 is 1 minus P. So we're generalizing, not requiring these to be equal probable at this point, right? So now our dimension here is 1, right? So we're just along the real line. And now we can look at this as a vector representation and kind of ignore the particular shape of the symbol, right? So we discussed briefly, we'll look at it in more detail later in the course, but we shape these symbols to match the channel. So okay, so I've set that up. Well, I think I can get this in here. The vector representations are now going to be as an amplitude, it's going to be the square root of the energy or the minus square root of the energy, right? So these S's are an amplitude, and the S square would be the energy or the power. Okay, let's take a quick break and I'll switch over to our other Zoom. Let's take like a 3-minute break or something. So
Okay, see you, sir.